easy assignment to introduce Jack Milnor, who does not need an introduction. So Jack will tell us his perspective on the dimensional topology.
Okay, can everyone hear me? So this is going to be a lightning tour through the centuries, so I have to speak at an average speed of 300 years per hour. So, but on the other hand, if I go too fast, if you want to hear more about some particular bit of mathematics or some person I'm talking about, please interrupt. I hope it won't do any harm. Okay, so I want to start out with the 18th century, a time before there was any idea of topology, but nonetheless there were some developments which suggested that there should be such a field. So the first famous question asked of Euler was whether it was possible to take a walk over the 7 bridges of Königsberg without repeating your steps. And you can represent this by a graph with each landmass as a black dot and each bridge is a connecting path. And the theorem was that there's given such a graph, there's a path traversing each edge exactly once, if and only if there are at most 2 vertices which are odd, in the sense that an odd number of edges come together there. This is for any of you who, if there's anybody here who doesn't know this theorem, it's a marvelous exercise. Very elementary mathematics, but still challenging. Okay, the next. So this was an indication that there might be a kind of geometry which didn't involve any notion of distance or angles, just somehow the shape of objects. And the next hint came from Euler again, who looked at a convex polyhedron and stated and later proves that the number of vertices minus the number of edges plus the number of faces is always equal to 2. So for example, in this case, we have 60 vertices and so on. Well, the first thing I described to you was perhaps important as a first paper in graph theory, but it didn't have much impact on topology. On the other hand, this has had a fundamental impact on topology. It's basic invariant, which comes up in many different places. So in the 19th century, one generalized it to any non-convex not necessarily convex polyhedron or cell complex. You can just count number of even dimensional cells minus the number of odd dimensional cells and get a number which seems to be invariant. And then in the 20th century, it was proved that this is a topological invariant. And the fundamental property is additivity property. If you take a union of 2 complexes, 2 subcomplexes, then you get the sum of the Euler characteristics minus the Euler characteristic of the intersection. So this is very convenient for computation of examples. Okay, that's, I guess, all I have to say about the 18th century. Now, in the 19th century, Cauchy gave the first precise definition of continuity, which is certainly one of the most fundamental concepts what topology is all about. And he also gave a marvelous example of a topological invariant, namely the winding number of a curve around a point in the plane. And he proved that it could be computed by an analytic formula integrating a holomorphic differential form around the path. Well, I said in order to say anything sensible, I have to concentrate. So from now on, I'm going to concentrate on the study of manifolds. So starting with 2-dimensional manifolds. Now, the first contribution that I know of was by Simon Weyl, who was the first, as far as I know, to study the Euler characteristic for non-convex polyhedra. And his statement was this: suppose you have a polyhedron in R3 which is pierced by n openings. Then the Euler characteristic is 2 minus 2n, where n is the number of openings. Unfortunately, the statement is very vague. What does pierced by n openings mean? And I mean, in a simple example like this, it's clear, but you can easily think of more complex examples where it wouldn't be clear. And unfortunately, we don't know what the original statement was, because when this paper was submitted, it was the publisher thought it was too long, so he abridged it himself. And all we have is the publisher's abridgment. But this n is a fundamental invariant, which is now called the genus of the surface. Something which really took me by surprise was the place. I had never thought of Geneva as an imperial city, but apparently for a few years it was part of the Napoleonic Empire. Well, this is a marvelous statement, but unfortunately the statement is very vague. The next one I want to talk about is Abel, who in fact, as far as I know, didn't do anything in topology, but what he did was introduced its ideas which made it clear that one needed something of the sorts. So for example, he was interested in the integrals of algebraic expressions like this one. And nowadays we would study this by looking at the smooth algebraic variety defined by this equation, so that the integrand is just dx over y, and differentiating the defining equation, we usually get this identity, so we see that it makes sense everywhere, not only when y is non-zero. And this defines a holomorphic one form or abelian differential on V. And for any closed loop on V, we can integrate. And we get a well-defined number which is invariant under homotopy of the path. So I'm stating this in modern terms, but in Abel's day, these words didn't exist. Well, he invented the concept of an abelian differential, but the fundamental group hadn't been defined. The idea of homotopy hadn't been defined. The surfaces hadn't really been studied. It was a completely open, an introduction to a completely unknown field. And Abel died very young before he could pursue these ideas very much, and it was left to other people to fill in the details. So the first person who really took up the challenge was Riemann, 30 years later. And these are some illustrations from Riemann's paper on abelian integrals. So the first is just a simply connected region in the plane. The second is what is called a doubly connected region in the plane. The third is a triply connected region in the plane. But he also considered more general surfaces which don't lie in the plane, but instead lie over the plane. So this is a surface of genus 1 which lies over the plane and is also triply connected. Well, I should say what he means by this. His definition was the surface is simply connected if any crosscut cuts it in two, any path joining the boundary to itself through the surface. And doubly connected if you can have one path which doesn't disconnect, but any two paths disconnect, and so on. And he also considered the case of closed surface. For example, a closed surface in the complex projective space, for example. And he described a procedure for cutting it open along a number of simple closed curves. And the key point is that these curves should intersect in just one point. And the cut open surface should be simply connected. So here's an example of the surface of genus 2 and 4 curves, which you could use to cut it open, so that the cut open surface looks like this. And then you can get the original surface by identifying the edges in appropriate pairs and with appropriate orientations. And the number of such curves is always an even number, 2p, or if we're going to identify them, well, no. So in this case, p is 4. So when we cut it open, there are 8 edges. But it always takes an even number of curves to cut a surface open this way. And this invariant p is a basic invariant described by Riemann, although he didn't name it. But it's what we now call the genus of the surface. Well, I must admit that I find Riemann very hard to read. He sort of waves his hands a lot and talks very fast. But I mean, it clearly inspired, he's inspired mathematicians ever since. There's no question about that. But still, it's sometimes hard to follow details. Oh, I didn't. 2p is the first Betti number. So here, this is the surface of genus 2, and the first Betti number is 4. So there's a presentation a few years later that I find much more readable, but it does have a limitation. Riemann was considering arbitrary surfaces, and Möbius considered only surfaces which were embedded in 3 space. He didn't make any comment about this, and it's not that easy to prove that an arbitrary surface can be embedded in 3 space. And in fact, it's only true if the surface is orientable. But in any case, this was a real progress because he gave a very clear presentation. So he defined the connectivity class as the smallest number such that any n disjoint loops necessarily disconnect the surface. Or I like to work with n minus 1. So we have p equals n minus 1 closed loops which do not disconnect the surface, but that's the maximum number you can have. And this p is, of course, the same as Riemann's invariant. And then, well, there's an example with p equals 1. So one loop does not disconnect the surface, but any 2 loops necessarily do. And his theorem is, well, he introduced a concept he called elementarily related. And his theorem was that any 2 closed surfaces with the same connectivity class are elementarily related. So I will give you some indication of what he meant by this, but I think in modern terms what he meant is C1 diffeomorphic. So this gave, at least if you restrict attention to closed surfaces in 3 space, this defines a single well-defined number which is a complete invariant. So here's his definition. 2 geometric figures are elementarily related if, well, you can read it for yourself. It's hard to make precise sense of it, but I think the good translation into modern terms is that it means that they're C1 diffeomorphic. And now the proof is amazingly modern. He embedded the surface in the, well, we assumed we had a surface in 3 space. Putting it in general position, he cut it by horizontal planes, and notice that, let's see, do I have a pointer here? I don't seem to be able to make the pointer work. Well, if you look at the top thing, you notice that it's a simply connected region. That the one with an A in it. The next one with a B in it is an annulus. The next one with a G and D in it is a pair of pants. And all of the others are just copies of these. So the statement is that you can cut it up into pieces which are of one of these 3 types. That is, each of these pieces is diffeomorphic to a subset of the 2-sphere. It either has 1 boundary curve, 2 boundary curves, or 3 boundary curves. So it's convenient for the proof to introduce more generally a notation for a subset of the sphere with connected region with any number of boundary curves, or EK, where K is the number of boundary curves. And what the preceding construction did was to cut the surface up into a disjoint union of copies of either E1, E2, or E3. So in this case, we have 2 copies of E1 and 2 copies of E3. And then to reconstruct the original surface, we just have to push these things together, matching. The labels have to be labeled, and the edges have to be labeled in pairs with appropriate orientations, so we not know what to glue onto what. And if you glue them back together, you'll get the original surface. Now, so here's a lemma. If we simplify this by taking 2 of these sets and identify one boundary curve of the first one with one boundary curve of the second, then the result is also something in the same family, with the number of edges will be the number of edges of K plus the number of edges of L minus 2, because we glued 2 boundary curves together. So let me illustrate this by going back here. If we, for example, take the I don't seem to be having any luck with the pointer, but if we take this little red disk and glue it into the red disk in the next figure, then we'll cut down the number. We've taken an E1 and E3 and pasted them together and get something with only 2 boundary curves. And E and 1 plus 3 minus 2 is 2. And similarly, if we take the black region to the right and slide it into the black hole, then we'll again get something with 2 boundary curves. And finally, I want to take this, it's supposed to be a blue boundary curve, and glue it into this blue region here. They don't quite fit, so we just have to shrink it, and then it will slide in. And when we slide it in, and remember that we've already gotten rid of 2 holes, it will have only 2 holes left. So that's the way the proof goes. So after a finite number of transformations like this, we obtain a set with only just a connected set with just some even number of boundary curves. And now here P is again the Riemann invariant. And now any further identification of 2 boundary curves, if we have a sphere with 2p holes of it and identify them in pairs, preserving the orientation, then we get what's called a handle body. For example, here, if we take a hole here and a hole here and glue them together, it's like adding a handle. Similarly for any. And clearly we can rearrange the holes as we like, so we get an essentially unique figure in this way. So that finishes the Möbius proof. Okay, the next name I'd like to mention is von Dyck, who a few years later was the first person I know of who actually gave a definition of what topology is. Namely, it's the study of properties of objects which are preserved under continuous homomorphisms with continuous inverse. And another fundamental contribution, he took the Gauss-Bonnet theorem and put it in a global form. Now, both Gauss and Bonnet had studied relations, a piece of surface bounded by a curve, and studied relations between the curvature of the boundary and the curvature of the piece of surface. But von Dyck, as far as I know, was the first one to put it all together and to get a formula for a closed manifold, which is the formula I think all of you know now, that the Euler characteristic is the integral of curvature with respect to area divided by 2 pi. And this has been an inspiration to mathematics ever since, especially to geometers who want to study the relation between topology and curvature. This is sort of the first model of what such a theorem might be. And there's an immediate corollary. Suppose that K has constant sign. If it's either always positive, always negative, or always zero, then we find that the Euler characteristic necessarily has the same sign. Okay, the father of modern topology in any reasonable sense is clearly Poincaré. He did so many things. Just introduced homology, embedding numbers, Poincaré duality, homotopy, fundamental group, covering spaces. And since I'm talking about surfaces, I especially want to emphasize the uniformization theorem for Riemann surfaces, which was something that he worked on for years, but finally proved only in 1907. So, at the same, Koebe proved it also in 1907. Some people like Koebe's proof better, but there's controversy about whether there's any real difference. Anyway, let me state the theorem. So if you take any Riemann surface and take its universal covering space, then it's conformally isomorphic to either the Riemann sphere, the complex plane, or the unit disk in the complex plane. Now each of these spaces has a natural metric. You can give the two sphere, of course, a metric of constant positive curvature. The plane has a metric of constant zero curvature, and the unit disk has a Poincaré metric of constant negative curvature, and these are preserved by the group of Dyck transformations so that they descend to the manifold itself. So the corollary is that any Riemann surface has a complete metric of constant curvature. So for example, if we take a closed surface of genus 1, it's +1. For a torus, it's 0. And for a higher genus surface, it's -1. Well, I've been using the term Riemann surface, but in fact, it wasn't very clearly defined in the 19th century. Riemann started with some sort of equation and took it all possible, some germ of an analytic function, we would say now, and looked at all possible analytic continuations and somehow fitted them together into a surface, but the definition was rather vague. And Hermann Weyl was the first to give a clear definition, precise definition of what a Riemann surface is in terms of overlapping coordinate charts. And this immediately served as a model for definitions of things like a differentiable manifold, a complex manifold. It formed a model for how to really put together local things and understand them in a global organization. So, of course, once this definition was available, people applied it to results which they'd used previously with a rather vague definition. Okay, I'm going to stop there in the discussion of two-dimensional manifolds and go on to dimension 3. So the first contribution was by Heegard, just before the turn of the century. He showed that any closed oriented three-manifold can be decomposed as a union of two handle bodies of the same genus, which intersect only along their boundaries. So here's a picture of a handle body. It's the same picture I showed before, but now you're supposed to think not just of a surface, but of the solid region in three space bounded by this surface. If we take two copies of this and then glue their boundaries together by, say, a diffeomorphism, and paste them together, we'll get a three-manifold. And the theorem was that any three-manifold, any orientable three-manifold, can be obtained by this construction. Well, one of the first applications, this is a very hard theorem to apply because there's so many ways of so many diffeomorphisms between a surface of higher genus and itself that it's hard to get a grip on them. But the first person to apply this was Poincaré, who asked this question in 1904. It's a question which drove topologists crazy for 100 years. Many of them.
Could I ask a question about Hagar?
Okay.
Where did the concept of three-dimensional manifold come from? Was that?
Well, let's see. Certainly people had been, algebraic geometers had been studying higher dimensional manifolds already, I believe. They come up naturally in algebra. I mean, if complex twofold is a real four-dimensional manifold. So, and I think Poincaré also had studied three manifolds. In fact, his first conjecture was that a three-manifold is uniquely determined by its homology. And I said that the first person to apply Hagar's theorem was Poincaré, because he used Hagar's construction to construct a counterexample to his first conjecture. That is, he found a way of taking two handle bodies of genus 2 and gluing the boundaries together to get something which had the homology of a sphere, but was not a sphere. So he was thus chastened, he changed the conjecture to the one which, as I said, drove people crazy for 100 years. Of course, another point I could make here, who was the first person to introduce an interesting three-dimensional manifold? I claim that was Dante. Because on the Divine Comedy, his description of the world where it took place, there was heaven was straight above us wherever we were. It was clearly a three-sphere where heaven was at the upper pole and hell was down at the lower pole, and the whole discourse took place within this three-dimensional sphere. But I don't think anyone picked up on that for a very long time. Okay, the next person I want to talk about is James Alexander. He, first of all, invented the Alexander knot polynomial. This was, people had been studying knots for at least 50 years, but this was the first time they had a real invariant which could distinguish different knots. And he proved the Alexander duality theorem, which was a far-reaching generalization of the Jordan curve theorem. So he knew now not only that a curve would split the two-sphere into two regions, but if you take any subcomplex of any sphere, if you know the homology of the subcomplex, you can compute the homology of the complement. So for example, any n-1 dimensional manifold splits the n-sphere into two connected pieces. And then he studied the special case of the two-sphere embedded in the three-sphere. He proved that if it's piecewise linearly embedded, then it separates the three-sphere into two piecewise linear balls. But then he showed that this piecewise linear hypothesis was really essential because he gave an example of a topological embedding of the two-sphere in the three-sphere, such that, well, the inner region is a topological ball, but the outer region is very far from one. He also proved another theorem which amazes me. If you take a piecewise linear torus in the three-sphere, then you can't say that both complementary components are copies of the solid torus because it may be knotted. But his theorem was that for any embedding of the torus in the three-sphere, one of the complementary components must be a solid torus. Okay, the next picture has nothing to do with topology, but I think it makes me think that it gives me some feeling for what Princeton was like almost 100 years ago. It shows Alexander together with my mathematical grandfather, Solomon Lefschetz, out for a drive. Okay, next, Hellmuth Kneser, in 1929, studied three manifolds and piecewise linearly embedded two spheres in them, and one consequence of his result is that we consider the following construction: giving two-dimensional manifolds, if they're oriented, we can cut a little piece out of each and glue the boundaries together to get another oriented manifold, another oriented surface. Or, well, you can do this in any dimension, but he was doing it in 3. And notice the sphere is the identity element. Here in the right-hand thing I've drawn there is topologically a sphere, and when you glue it on, you get something which is still topologically a sphere. And what he proved is that, the definition, if you have such any decomposition except this trivial one, then it's called a non-prime manifold. If this is the only way of decomposing it, then the manifold is called prime. So that, in other words, it's prime if any time you split it in two with a sphere, one of the pieces must be a topological disk. And the theorem is that every compact manifold is isomorphic to a connected sum of primes. Now this may look obvious at first. If it's not prime, then it splits as a sum. And then you take either of the sum ends, it's either prime or it splits as a sum. So the only problem is to prove that this procedure stops after a finite number of stages. So many years later, I was looking at this problem and I got completely stuck at this point. And it was very embarrassing to discover that Kneser had solved it before I was born. But I did make a further contribution showing that these manifolds are unique up to order and up to isomorphism. So there's a unique decomposition into primes. I should mention that we're getting into a very dark period in history. In fact, Kneser was a supporter of the Nazi Party at a very early time. There were a number of German mathematicians who produced beautiful mathematics, but were also strong supporters of the Nazis. What can one say? Okay, back to Princeton. Christos Papakyriakopoulos. He gave the first proof of Dane's lemma. This is the theorem that suppose you have a closed two-disk and a piecewise linear map, not a homeomorphism, but a map into the 3 space, which is well behaved near the boundary, then there exists a piecewise linear embedding which coincides near the boundary. So if it bounds a singular disk, then it bounds a non-singular disk. This result had been claimed much earlier, but the proof was wrong. So as a corollary, suppose you take a piecewise linear simple closed curve and suppose that the complement is simply connected, then it's easy to span a singular disk in it. And by his theorem, you could then span a non-singular disk, proving that it was unknotted. It was a very ingenious proof, which he avoided the difficulties which Dane had had by passing to a sequence of tower of covering spaces until he simplified the situation enough to solve it. Okay, the next theorem I want to mention is noteworthy in that it seems to have nothing to do with topology. So suppose you have a closed manifold of dimension 3 or more with constant curvature -1, then it's uniquely determined up to isometry by its fundamental group. So this is a theorem in pure geometry. There's no mention of anything to do with topology here. If you like, it's a theorem about actions of a discrete group on a homogeneous space. So group theory and such topics. But it has a marvelous application because the corollary is that we get topological manifolds whenever we have I'm sorry, that we get a topological invariance whenever we can put such a metric of constant negative curvature on a manifold. So this, if you just start with a manifold which has a negative curvature, then its fundamental group determines everything. It determines the eigenvalues, the Laplacian, lengths of closed geodesics, any geometric invariant you can think of. But the volume is especially convenient because it's just a single positive real number. It has nice properties under covering spaces. For example, if you take an n-fold covering of the manifold, then the volume just gets multiplied by n. And it would be very nice to understand the numbers which arise this way. But in fact, very little is known. So for example, if you're given two manifolds, and you can presumably compute their volumes, but how do you decide whether the ratio is a rational number or not? And if the ratio is rational, how do you decide whether they have a common covering space? Well, this led to a great deal of interest among topologists. The first person was Robert Riley, who was a graduate student in England at the time. He was an American, but a graduate student in England, who showed that the complement of the figure 8 knot in the three-sphere has a complete hyperbolic structure of finite volume. And Troels Jurgensen found more examples of, in this case, of compact manifolds with curvatures of -1. I should say that there were known examples much earlier, but just a few very isolated and special examples. These were general examples showing wide classes of manifolds with constant negative curvature. Bill Thurston found many more examples, and he also computed the volume of the figure 8 knot by triangulating it into two regular ideal simplexes. So ideal means that simplexes with the vertices missing. So, or in simplexes in hyperbolic space with the vertices on the sphere at infinity. And in that way he could, such things had been studied all the way going back to Lobachevsky, and he could give a complete formula for the volume in terms of integration of a classical function. And a few years later, he produced some amazing theorems in this direction. First of all, he showed that the possible volumes of hyperbolic three manifolds form a well-ordered set. So if you're given any collection whatsoever, not necessarily finite, of three-dimensional hyperbolic manifolds, there will always be one with smallest volume. And he proved that this volume is almost a complete invariant. And if you're given the volume, there are only finitely many possible manifolds. And there's another more explicit description. Suppose you have a manifold with k ends. Maybe I can use the blackboard. So if you think of a hyperbolic manifold with finite volume, which is non-compact, then it has to go out to infinity. But it has to go out to infinity in a very thin spike. There may be several such spikes. But they all have to be very thin in order to have finite volume. And if you take a cross-section of one of them, there's only one possibility. It has to be a torus. Remember, this is a three-dimensional manifold, so this will be a two-dimensional cross-section. So if you have a non-compact manifold with finite volume, then it will have finitely many of these spikes going out, which I'm calling ends, or sometimes they're called hyperbolic cusps. And then what you can do if you have such a cusp is just cut it off and glue in a solid torus. And what he proved was that in most cases, the manifold you get again has a complete structure of hyperbolic volume, but it's always larger than the volume of the non-compact manifold. So you always get, if you do this, you get an increasing limit of manifolds with fewer ends. So here's an example. Suppose you take a Whitehead link. This is a specific example of a link in the three-sphere. If you remove it from the three-sphere, you clearly get two different ends, each of which is, in the red torus and the blue torus you can think of the boundaries which you can cut off. You can take either one of them and paste in a solid torus in infinitely many different ways, and therefore you get two integer parameter family of hyperbolic manifolds. In this case, this is the volume, so all of these other manifolds have volume less than this number. And if you take any infinite sequence of them, well, a bi-infinite sequence with filling in both edges, then it will converge to this number. Well, here's another contribution, just again in the 70s. Jacob Schalen and Johansson studied, in general, decomposing a piecewise linear manifold by cutting into simpler pieces along tori and spheres. And they showed that there was an essentially unique decomposition into which each piece was either couldn't be further decomposed or was what's called a Seifert fiber space, which is a class of three manifolds which is well understood. And then in the 80s, Thurston discovered this very bold, or introduced this very bold conjecture that every smooth closed three manifold can be decomposed into pieces, each of which has a homogeneous geometric structure, or locally homogeneous geometric structure. So you can cut it up by spheres and tori into one of 8 possible, each of the pieces, so that each of the pieces would have one of 8 possible geometries. And since I'm let me just go through this very fast. There's positive curvature, zero curvature, negative curvature. These are the 3 obvious possibilities which have been studied for a long time. And the next 2 possibilities are also pretty obvious. You can have circle cross 2-sphere, or circle cross a closed hyperbolic manifold. These also have a homogeneous structure in an obvious way. And the last 3 are much less obvious. They're all examples of 3-dimensional Lie groups with a maximally symmetric left invariant metric. There's first of all the nil geometry with this group, for example, circle bundles over the torus. There's the solved geometry with this group. The example would be torus bundles over the circle. And finally, there's the geometry of the universal covering space of SL2R. And a typical example would be the unit tangent bundle of a hyperbolic surface. So his theorem, or his conjecture, was that any 3-manifold could be cut up along spheres and tori into pieces, each of which has one of these structures. And that this decomposition was essentially unique. Well, Thurston proved this example in many cases. Well, I won't go into technical details, but there are many classes of manifolds for which he was able to prove it. But the hardest case, the general hyperbolic manifold, or the general spherical manifold, with a general manifold with finite fundamental group, he was not able to handle. So this is another example. Mostow was the first of a using methods which have nothing to do with topology and yet which made very important contributions to topology. In this case, it's the Ricci flow equation, where GJK is the metric tensor of a Riemannian manifold, RJK is its Ricci tensor, and this, you just vary the metric according to this equation. It's something like a heat equation, and the intuitive idea was that curvature should spread out evenly so that in the limit you should converge to a surface of constant curvature. And in some cases, Hamilton was actually able to prove this. If he started out with a space of strictly positive Ricci curvature, he could prove that it converged to a real, honest sphere, the standard sphere. So this was a new result, which is proved by this method. But in general, the problem is that this Ricci flow leads to all kinds of singularities which are extremely hard to handle. And what Perelman was able to do was analyze all of the possible singularities, and so some of them would correspond to things would decompose along. If you have a thing decompose and shrink to a two-sphere, so this would correspond to a Thurston decomposition of the manifold by a two-sphere, or sometimes it would correspond to a decomposition by a torus, and other times he showed that the singularities could be ignored. So somehow he pieced it all together and gave a proof of the full Thurston geometrization conjecture, and in particular, applied to I should have said that this, I see. He proved the full conjecture, including the Poincaré conjecture, because it's a special case. If we have a simply connected manifold, the conjecture implies that it is the standard sphere. Okay, so I have a few minutes to talk about four manifolds. So the first contribution I want to make is by Henry Whitehead. Well, as you may guess from this picture, he's the only mathematician I ever met who had a hobby of raising pigs. But again, he had a theorem which had nothing to do with manifolds. He was interested in studying the homotopy type of complexes. And so he considered simply connected four-dimensional complexes and gave a complete set of invariants for their homotopy type. So a few years later, I noticed that this could be applied to four-dimensional manifolds and gave a very simple homotopy classification of simply connected four manifolds. Namely, all you need is the intersection form. So if you have two-dimensional homology classes, you can intersect them and get an integer, assuming everything is oriented. And this is always a symmetric bilinear. And according to Poincaré duality, it's unimodular, that if you choose a basis for H2 and form the symmetric matrix, it has determinant plus or minus 1. Well, the classification of such forms is an important problem in number theory, and it's highly non-trivial. It turns out that if you have an indefinite form, that is, if the self-intersection takes both positive values and negative values, then the classification is quite easy. But if it's positive definite or negative definite, then it gets to be very difficult. And the problem is as the Betti number gets larger, as the size of H2 gets larger, you get more and more examples, so it grows enormously. Carl Ludwig Siegel showed how to estimate such things, and in this, he showed that the number increases very rapidly. As an example, suppose we take rank 30, so the second Betti number equal to 30. Then he showed there are more than 900 million distinct examples. Siegel was an amazing person. According to André Weyl, he was the most important mathematician in the first half of the 20th century. And this was a marvelous exercise finding an analytic lower bound for the number of unimodular forms. But I couldn't give you details if I wanted to, but it's clearly a very important result. Okay, next example. Back to Russia was Vladimir Rochlin, who proved the following theorem. Suppose you take a smooth closed four manifold with positive definite intersection form. And suppose that the self-intersection takes only even values. Then the rank of this form must be divisible by 16. Now, well, you could try to see what you could do just by straight algebra. So suppose you just have a symmetric bilinear form which is positive definite, unimodular, and takes only even values. Then you can prove algebraically that it must be divisible by 16. So he just got an improvement by a factor of 2. But in fact, this is an amazing result. In some sense, it's the beginning of the whole field of differential topology, because you notice the hypothesis there that the manifold is smooth. Now, at the time, one assumed that this was just a technical point, that it didn't really matter, but it turned out that that was the crucial assumption. And the methods he used were forerunners of the methods of differential topology, studying characteristic classes, relations between them, and relations with the topology. So let's see, I don't know whether I said this right before, but if you just look at the algebra, you can get anything which is a multiple of 8. The simplest example is given by this E8 Dynkin diagram, where each dot stands for a basis vector with self-intersection number 2, and each edge stands for saying that the inner product of the two basis vectors is 1. And if there's no line between them, then they're orthogonal. So this describes a unique matrix which has determinant +1 and rank 8. And by Rochlin's theorem, this example can never occur as the intersection matrix for a smooth 8-dimensional manifold.
So Rochlin, is this just a simplified version of his statement? He did it for signature and indefinite forms also, or did he only consider the definite case?
No, this is a simplified version. I think he proved. Mm-hmm. Okay, back to Leningrad, where we live, but 50 years earlier than Perelman. Markov proved a rather devastating theorem. This is the son of the more famous Markov who invented Markov chains and so on. Problem of classifying closed form manifolds up to homeomorphism is algorithmically unsolvable. And he did this by, given any group described by finitely many generators and relations, he constructed an appropriate four-dimensional manifold. I guess this had actually been done much earlier, but he found this application for it. And he showed that two of these manifolds were homeomorphic if and only if the groups were isomorphic. On the other hand, it had recently been shown that the isomorphism problem for groups given by generators and relations is unsolvable. So the conclusion was that if you're going to have any chance of a reasonable theory, you can consider only manifolds with known fundamental group. There's no hope of having a general theorem of the kind we have for three manifolds, where you don't have to worry about the fundamental group in some sense. That is, the fundamental groups of three manifolds are somehow tightly restricted so that you don't run into this problem, but for four manifolds there are no restrictions. Okay, next contribution, Michael Friedman in 1982. he proved that a closed-oriented, simply connected four-manifold is uniquely determined up to homeomorphism by its bilinear intersection form, the same one I've been looking at, together with one mod 2 invariant, which had been introduced by Rob Koebe and Larry Siebenmann. This was Koebe-Siebenmann's invariant is an obstruction to smoothness, so for a smooth manifold, you don't need it. It's always 0. So a smooth four-manifold is completely determined up to homeomorphism by its intersection form or by its homotopy type. And he proved that any symmetric bilinear unimodular form can be realized by a topological manifold. So, for example, he could construct a topological manifold which realized this E8 example, and according to Rochlin, this cannot be smoothed, or according to Koebe and Siebenmann, it cannot be smoothed. So we had examples of four-dimensional manifolds which were constructed topologically and yet which could not have any smooth structure. And his methods were using what I consider very wild topological methods. This is one of the version of his proof is based on the concept of a grope, which is illustrated here. So this is trying to solve the analog of the Dane's lemma problem. In a three-manifold, if you have a simple closed curve which bounds a singular disk, which is homotopic to a trivial, represents the trivial element of the fundamental group, then it bounds a good disk. But that turns out to be not true in dimension 4. Instead, you have this approximation. So you start with the simple closed curve on the bottom. If it's represents the trivial element of the fundamental group, then it certainly represents the trivial element of the first homology group, so it'll bound some kind of surface. In this case, it's bounding a surface of genus 1. But then you have the problem with the fundamental groups represented by the curves around this surface of genus 1. So for example, you have a curve in the middle there, which is non-trivial. So you apply the same construction again, and it is the boundary of some kind of surface, in this case of genus 2, and then you find curves in the surface of genus 2, so they bound, and you consider continue ad infinitum. This is called a grope, and was invented by Jim Cannon, and is a fundamental tool and one version of Friedman's proof. An alternative version of the proof uses the concept of the Casson, Andrew Casson's handles, which are similarly wild objects. Okay, now we come to the next year. That was 1982. Then 1983, Simon Donaldson's thesis proved the following amazing theorem. If a smooth, closed, simply connected four-manifold has positive definite intersection form, then this form is diagonalizable, and hence by Friedman's theorem, it's homeomorphic to a connected sum of complex projective planes. Now, I've given two examples already of fundamental contributions to topology which were based completely on non-topological methods. This is a third one. This is based on very deep analysis and rather easy topology. Oh, well, let me just give an example of the theorem. So suppose we look at these more than 900 million topological manifolds constructed by Friedmann with a positive definite intersection form of rank 30. Of all of these, according to Donaldson, only one is represented by a smooth manifold. Well, I can't say much about his method, but it's based on instanton theory, gauge theory. He looks, given the form manifold, he looks at a certain bundle over it with this special unitary group SU2 as fiber, and he looks at self-dual connections on this. That is, such that the curvature form is its own Hodge dual. And he studies the space of all these connections, modulo gauge transformations, automorphisms carrying each fiber into itself, and proves the result is a smooth 5-manifold with a finite number of singularities, each of which is a cone over projective space. And this manifold has a compactification by putting the original manifold M as on it to an infinity, so he constructs a cobordism that way and computes that the computes the signature of the manifold and completes the proof. I don't think I can say any more now. Okay, I'm running out of time, but just this combination of two different methods from mathematical physics and methods from hardcore topology, seem to be totally incompatible, and they led to amazing consequences. For example, Cliff Taubes proved that the Euclidean space can be given uncountably many distinct differentiable structures. And this is sort of amazing because in every other dimension, it's known that the Euclidean space has only one structure up to diffeomorphism. So 4-dimensional topology is really different. Well, let me just conclude that there's a lot one doesn't know about 4-manifolds. The problem is that smooth 4-manifolds are still very difficult objects to study. So the Poincaré problem for smooth 4-manifolds is completely open. Now, what you can say for any dimension is that the manifolds homeomorphic to the sphere form they have a well-defined connected sum operation. It's commutative and associative, so we have a well-defined commutative associative semigroup. It's clearly at least countably generated. And for all other dimensions, it's a finite abelian group. But for 4, in many cases it's trivial, but quite likely in most cases it's non-trivial. So these are dimensions of which the smooth Poincaré hypothesis is known to be true, but it's usually not true. And for dimension 4, it's completely unknown. Is it a trivial semigroup? Is the smooth Poincaré conjecture true in dimension 4? If it's not trivial, is it at least a group? If it is, how big a group? If it's not a group, what kind of semigroup it is? All of this is completely unknown, and I'll end there. A few representative references.
Comments?
When was PL first introduced?
Well, I mean, I can answer. I'm not sure what you mean by PL. I mean, certainly the idea of a non-convex polyhedron, just say any union of finite convex polyhedrons, was introduced very early. But the notion of a PL manifold, you mean?
Yes.
Yes, okay, so this is the question. You have a notion of PL homeomorphism. It's a homeomorphism preserving piecewise linear structure. And a PL manifold is one which has local charts which are PL homeomorphic to Euclidean space. Now this is a basic concept, but I'm not sure who first introduced it.
The difference between the piecewise linear and local structures, so essentially.
Okay, that's true. So the Hauptvermutung was the conjecture that if two complexes were homeomorphic, then they had isomorphic rectilinear subdivisions. That turned out to be false. But that doesn't answer the question of who first introduced the concept of a piecewise linear manifold.
Well, combinatorial manifolds were known in the 20s to Van Kampen, but the word PL was Riemann.
I see. Thank you.
Yeah, sorry,
Well, let me just repeat what Andrew said, that Van Kampen had introduced the idea of a combinatorial manifold, which is essentially equivalent. That was in the 20s? Or?
Yes.
And then Riemann introduced the term PL. Thank you.
You had cited Guard in the language of PL manifolds. That's 1890 something.
Well, I was cheating. I think first of all, he did a great deal of hand waving. And what he did was more in the differentiable category.
Yes.
But nowadays, it's easier to think of it in the PL category. So
Now, I actually have two questions, one in dimension 3 and one in dimension 4.
okay.
So in dimension 3, Ricci flow was studied by the physicist Dan Friedan
Mm-hmm.
in the early 80s, and I was wondering if he was it inspired Hamilton, or was Hamilton at all motivated by Friedan?
I don't know the answer. Does anyone know?
So there is something that's like Ricci flow that comes out of, I guess, the renormalization group.
Well, Friedan was studying the renormalization group.
Right. So but you don't literally. Right. So you don't literally get Ricci flow. You get something which is like it plus.
Well, yeah, but at long distances, that's the leading term, and so Dan was definitely interested in that, and in the supersymmetric case, you actually get Ricci flow.
So I think that it's probably independent. The key thing is to look at when did Hamilton start looking at Ricci flow on Riemann surfaces? I think it's a little bit older.
Yeah, then the question is, what was Hamilton's motivation?
Richard told me once that he wasn't aware of what Friedan had done. And in fact, when he first wrote down his version of the equation, he had the sign wrong, which a physicist would never do because they know how it's supposed to flow. So he wrote it down with the wrong sign. He started studying it, and all hell broke loose, and then he realized he had the sign wrong. I think he was motivated by minimal surfaces and minimal surface flow, harmonic flow on minimal surfaces. He was trying to do a geometric version where it's the metric that's moving rather than submanifolds, which is something we do a lot.
I think for the harmonic flow, Jim Niels was some of the correction. I don't know much about it.
I also have a question in dimension.
Well, just let me make a comment about that. Of course, when you get the sign wrong in Ricci flow, it's like having the sign wrong in the heat equation. So heat flows from hot to hot and from cold to cold, and everything blows up.
You notice there was a minus sign in your equation.
Yeah.
Because of the normalizations we used.
Yeah.
So that's why he wrote it down wrong. He realized that he was doing the heat equation backwards.
Okay, sorry.
Dimension 4, what's the relationship between the PL and the smooth category?
It's very close. Let's see, in general, there's an obstruction theory for passing from PL to smooth, and the obstruction groups are essentially, well, the groups of equivalence classes of diffeomorphisms of spheres. So in all dimensions other than 4, this coefficient group is well known. It's trivial up to dimension 6 or so. But also in dimension 4 it's trivial because of a theorem of Smale, which says that every diffeomorphism of the 3-sphere is smoothly homotopic to a rotation. So in fact, for 4 manifolds, there's no obstruction.
Any other questions, comments? Let us just again.